AP Style Free Response Problem 2. A sample of SO3 is placed in a 5.00 liter rigid container at 25 degrees C. The initial pressure of the container is 2 atmospheres. Sulfur trioxide is known to decompose by this reaction. 2 SO3 gas decomposes into 2 SO2 gas plus O2 gas. This graph shows the pressure of the container after the reaction starts. Okay, so it starts at 2 atmospheres, and you can see what happens as time moves forward. A, what is the equilibrium pressure of each gas at equilibrium? So we're going to use the graph to determine the pressure of the container once the reaction reaches equilibrium, when the pressure reaches a constant value. This is the red line on the graph. The total pressure of gas in the container at equilibrium is 2.6 atmospheres. An ice chart is used to find the pressure of each gas on the next slide. This is Free Response Problem 2, Part A continued, where we're finding the pressure of each gas at equilibrium. So we set up this ice chart to provide the expressions to determine the pressure of each gas that comprises the total pressure of 2.6 atmospheres. Remember that this was read from the graph at equilibrium. Okay? So we're told that the initial pressure of the container, which is only sulfur trioxide, is 2 atmospheres. We have no pressure from the other 2 products. The change based on the stoichiometry for the SO3 is minus 2x, for the SO2 is plus 2x, and for the O2 is plus x. So at equilibrium, we would expect 2 minus 2x atmospheres of pressure for the SO3, 2x for the pressure of the SO2, and x for the pressure of the O2 at equilibrium. First, solve for x, and then use that to solve for the pressures. So to solve for x, the total pressure is just the sum of each of the partial pressures, SO3, SO2, and O2. So we just substitute the pressure for SO3, 2 minus 2x. The pressure for SO2, 2x. And the pressure for O2, x. So 2.6 equals 2 minus 2x plus 2x plus x. If we simplify that, we get 2.6 equals 2x, 2 plus x, or x equals 0.6 atmospheres. Once we know x, we can put that back in each of these places to solve for the pressures. So for SO3, 2 minus 2x, 2 minus 2 times 0.6 is 0.8. 2x for the SO2 is 1.2. And O2 is just x, so 0.6 atmospheres. Part B, what is the value of the equilibrium constant Kp for the reaction? So we're going to use the gas pressures from Part A to calculate Kp. The thing to think of in these AP problems is each part is always leading you to the next part, to the next part, to the next part. Okay? So we write a Kp expression. Kp is the pressure of the SO2. So remember, it's products over reactants. So SO2 squared times the pressure of the O2 divided by the pressure of the SO3 squared. Again, we've got these coefficients, can't forget them. And then these are the values from Part A. So all that's left to do is just substitute the values. 1.2 squared times 0.6, which is 1.44 times 0.6, over 0.8 squared, and we get 1.35 as our value of K. Part C, what was the percent decomposition of the SO3? So let's think about what we know so far from parts A. We know how much SO3 we started with, or what pressure we started with. And we know the pressure at equilibrium. We determined it in part A. And so we can calculate the change in the percentage change in pressure of the SO3. So remember that initially we had 2 atmospheres of pressure. At equilibrium, we had 0.8 atmospheres of pressure. So the percent decomposition, the initial pressure minus the equilibrium pressure, so the part that was the change divided by the whole, the initial, multiplied by 100%. So 2, our initial pressure, minus 0.8 atmospheres, our equilibrium pressure. So that means our change was 1.2 atmospheres divided by the initial pressure of 2 atmospheres times 100. So the percent decomposition, how much did the SO3 decompose? 60%. Part D, about when does this reaction reach equilibrium? This is just some more graphical analysis. In part A, we used graphical analysis to determine that the equilibrium pressure of the container was 2.6. Now we're going to determine when this equilibrium happens by finding the time on the graph when the pressure reaches 2.6 atmospheres. I've drawn a green vertical line here to estimate this, and it occurs at about 21 seconds. Something to note about these graphical analysis problems. When you have to estimate from the graph, they always give a range of values. So maybe for this one, it would have been 21 to 22 seconds, let's say, would have been an acceptable, or 20 to 22 seconds would have been an acceptable answer for this problem. But this happens at about 21 seconds. Part E, how would the value of the equilibrium constant you calculated in part B be affected if the container developed a leak during the experiment? Justify your answer. So first of all, we have to think about what is the impact of a leak on the container. That allows the gas to escape, and the container can't maintain its pressure, right? So the pressure of all the gases would fall proportionally due to a leak. If this pressure decreases in the denominator, that would increase Kp. As the numerator decreases, that would decrease Kp. But in this expression, the impact on the numerator would dominate. Why? Because on the top we have a cubed term, we have a square times another value, while the change in the denominator would be squared. So in other words, the change is higher, the impact in the numerator is greater. So if this decreases, if that pressure decreases, then Kp would be reduced by the leak.